So I've got one of my holders for my mirrors. Oh, it's right there. Okay, so I got those done. Actually, I could show you that. You can't really see it that well. This is a filed down cutout of where am I? Of a mirror holder. And so I still have to draw, I have to drill the top of the mirror is actually going to come up a little bit higher. Where's my, I don't really have my ruler handy, but it's 2 inches by 2 inches. And so the reason why this is wider is because I'm actually using, I'm going to have like a cushion. It's going to go inside of this on both sides. And the cushion is it's made of like a foamy type material, whatever it is, right? So the mirror is going to set in there so that as much of the 2 inches of the mirror is accessible as possible. As far as I can tell, so the support, there's like 2 support rods that go down the aisle. I can even show you one of those. Actually, they're sitting right here. This is a support rod. It's a threaded 1024 rod, and so that's going to comprise. That'll comprise of like this is like the top support. Okay. And so this will have a nut and a slider on it. And so what's going to happen is that this mirror support holder is going to have 2 holes drilled up on the top right here. Very small holes, just small enough to support a spring. And so what that spring's going to do, it's going to, I'll show it to you this way. So like pointing at you, right? The spring is going to be supporting the mirror. And this is the top pole. It's going to be 2 of them, top rods, and they are threaded. These will be locked into place, and then I'll have two more rods on the bottom that are actually, they're going to have springs as well, so that the mirror holder is actually going to be about 45 degrees down, down bubble, and then 45 degrees off of this one here on the bottom. Now sideways, oh shit, don't drop my Mikey. Mikey, get back up here, Mikey. So on the bottom, so what happens is, this is going to be supported like this, and this to be 45 degrees here on the bottom. So the way that's going to work is that the spring on the bottom, it's also going to be, wait, let me think about this. Okay, so, yeah, okay, so that's going to be locked into place. Now, the springs on the bottom with holding this mirror at 45 degrees, those are going to be tunable. So what happens is there's a nut here, and then there's like a spacer, okay? And so the spacer acts like a little spacer, right? But, you know, so that the nut's not right up against the thing here. And so I got a room to get my thumb in there at the bottom. And so what that does is it does a coarse tuning. And so this mirror, like if you do one side, it's going to get skewed, right? So the idea is to get 45 degrees even on both sides. And so you send a laser beam down through the middle, and it goes down, and you know, you line up the laser beams that way. Those are the coarse adjustments. Now, the fine adjustment, I just found some plastic for my support beams. And so the support beams are going to come like vertical like this, and they're going to hold the end of these rods, the one on the bottom and the top, and the springs are going to come off. Well, what's going to happen is there's going to be like a support piece that goes on the bottom, which I don't have here. There's like a support piece on the bottom, and it has a flat piece on the end. I actually found something else just recently but you can't put the springs in there. So you got this plastic on the end, and it's going to have this flat end right here. It'll be like flat. Let me just see if I can. I don't know if that's messing up over here because I can't quite see it without messing away. You probably can't see it that well, but it doesn't matter. So the rod's going to be down here on the bottom, and the coarse adjustment is made. So then what happens is there's another piece on the end of the rod that's supported by two springs on the support beam, and there's a flat piece on the end of the rod. And so the springs, you know, this is kind of heavy. I don't know exactly the weight of the springs yet. Haven't quite figured that out because I haven't, you know, this is going to be supporting two mirrors at a certain weight. And even before I get these mirrors out, I'm going to develop I've got some first surface mirrors that I want to cut. And I don't know what the weight is on them, but I'm going to measure the weights of the mirrors and everything so that with the two mirrors, I know the exact weight and everything. And, you know, I can do that kind of thing. I want to just jump this music up here a little bit. And so what happens is at the end, there's another screw. This is 1024, and the other end is going to have a tuning screw. It's called a 440. It's a very thin screw, and so that's going to be on the wall, and that's going to have an entry point sticking through where the tuning rod is down at the bottom. So the rod's going to be like over here. It's going to have this flat piece, and the tuning screw is going to be up against the flat piece on this rod. And so what happens is there's going to be tension on both sides of the rods with the springs. So what happens is that because of the tension and the very close proximity of the alignment of the laser with the coarse adjust, I can use the 440 screw and I can push against that flat piece. And so maybe what I'll do is, because I'm pushing against it, and that's going to make the laser beam go, you know, like this, I may coarse set the laser beam ahead in preparation for the fine adjustment to push it forward. There's I think it's a plus and minus 1/8 of an inch I don't think it's a quarter. It might be plus or minus 1/8 of an inch or something like that for the fine adjust. I forget. But yeah, I was reading about that this adjustment needs to be around 2 microns or something, right? And so it's a screw, and so the 440 screw is like you know, you're not going to notice anything, but where the laser beam is coming down, it's going to be all aligned with the camera and everything. You're going to notice it, right? So that's kind of that thing. And I got 2 of these done, but I still have to do one for the beam splitter. And then, like on the map here, you can see the beam splitters, like sort of like that yellow box between the green triangle and the one at the top on the right there. That's the I'm pointing at the wrong thing. That's the beam splitter. It's that upside down thing. Actually, no, I take that back. Now, hold on. Okay, so the green one at the bottom, middle, that's the main beam splitter that sends the signal through the tuning cavity, which goes kind of out towards the left or whatever. That's a separate. That thing on the right there is actually a separate diagram. Let me just let's take this one here and do this, and maybe do that. Yeah, let me just draw a line here because this is not part of this stuff that's happening here. We'll just do a little thing here to kind of separate that. So you got the tuning screw and that kind of stuff. So then the beam splitter is going to it'll have the rods like this, and I haven't really designed this yet. I want to get the other 2 in place. So the beam splitter is also going to be on a device like this. It's planar, it's not a prism type device. And so that one's going to be held on by gravity. It's going to be pointing like this, so it'll be like this probably. The end support, I guess, so there's going to be an end support. I didn't even figure this out yet. So the end support's going to be over here along with the other beam that's going across. There'll be an end support, and that end support's going to be a little bit higher. Maybe I'm going to use a wire or something down towards the spring, or I don't know exactly how I'm going to do it yet. Doesn't really matter. But the entire support section is going to be on a movable platform, and so the supports for there's going to be supports for these things, and those supports will have the springs attached to them, and so all of these rods are going to be supported by springs. So there's actually going to be 3 layers of vibration absorption into the mirrors. There'll be these springs on the rods. There'll be the springs from the rods to the holders, and then there's the foam from the holders to the actual mirror itself. So this one being pointed this way, it will have, can't really hold it very well, it will have lock settings up here, like this will be locked here at the top, and then the adjustment is going to be down here. So probably what I'll do is I'll have, this is the adjustment rod, and so that will probably be up at the top. This is like, there's only 2 inches from here to the top of the case. So what I'll do is I'll have an adjustment point at the top of the case coming down onto this rod. It'll follow the same idea as the one's going sideways. So that really shouldn't be a problem for me to do. Now, that's kind of that little update. And so I'm going to make another one of those. No big deal. I don't really have the plastic. I do have the plastic. I have plenty of plastic. I took some stuff apart. Like, all of this stuff just came together within, like, 5 days. You know, it's like I'm thinking, okay, this, and this, and then it actually took me 2 or 3 days to figure out how to support the mirrors. So, the idea, there's a new idea, and I found this on a website learning about spectrometers. And it kind of makes sense. But if I use this entire setup here, I got these distances to play with. Now maybe this second beam splitter between the yellow line at the top and the green triangle at the bottom, it may actually be smaller. I don't really know yet. I'm assuming because I'm not going to use my main beam splitters for that. I don't think. I don't really want to cut them. So I've got that's not a beam splitter, I found some new optics, and I think the beam splitter is quite small. It's only like this. Let's see, so there's 1.5 inches from the top, so from the top down to the bottom of that first mirror on the top there, so it's 1.5 there. I've got this cylinder is 3 inches, so I've got 1.5 from the top of the cylinder to the center, and I've got 1.5 from the top of the beam splitter to the top. Okay, so that means 0.75 from the center to the top, and over on the cylinder I've got 1.5 inches. So 0.7 into 1.5 leaves me another 0.75. So I've got 0.75 inches from the top of the cylinder to the top of the beam splitter. I have used 1.5 there, 1.5 and 0.75. That entire distance, I think. So from the beam splitter down to the bottom, I was trying to get 12, but I've got 11 inches. So maybe I'm using 10. So assuming I'm using 10 inches, that gives me 1 inch of freedom. And so 1.5, that's 2.75 and 0.75 is, no, that's 2.25, I think, or something like that. It's like 2.2 inches from the top to here. Well, actually, you know what? It's 0.75. Yeah, you subtract. Well, I added an inch. I made that 2 inches. So that's actually 1 inch from center. 1 inch from center and 0.7. So that's 2 inches. We could actually say, well, it's 2.75. So you take half of that. Well, I don't know where this other beam splitter is going to be, but honestly, it needs to be at a halfway point, right? So you're talking it's 2.7. 2.7. It's half of 2.7, so that's 1.6.7. 2.25. Okay, and then half of that, 1.25, and half of that is 0.625 inches. So, the new idea is we're gonna let's grab this color here, and we'll grab this line here. And so the light source control there's another mirror. All right, let's see, let me go back to that and draw another mirror, but it's not really, you know, I could probably draw it like way the hell over here or something. So let's draw the mirror here. And we grab a circle and we do the light source up here, let's say. And then we're going to take this purple. I'm going to draw another line. And we're going to draw it. I don't know exactly where this is going to be. I think it was supposed to be somewhat close to this slit. But it's actually, this is going to be outside of the case in another. I'm going to exaggerate this picture here that I'm drawing. This is a slit opening, okay? And then so there's one there, and then we can take this yellow line, okay, make some smaller lines, and we can go like, what's going to happen? Like the light beam comes in here, and then, you know, it kind of spreads out. There's things that there's an interaction pattern now. Okay, it kind of spreads out and shit. All right, so now that light beam goes over yonder, over here, and we just make a little arrow, and there's a bunch of lines going over there, yada yada. So okay, there's that. So then go back to the purple, and now what happens? What is needed is halfway between that second, assuming that there's a second one there, is another slit. No, that's not a very good one. Damn. Okay, so let me redo something here. I hope I can do it now or not. I think I screwed it up. Shit. Let me do black. Let's do set that line. Hey, cover this up. Get lucky there. I want to leave a space to exaggerate it's crooked. Okay, so big fucking deal. It's crooked. All right. So I saw this in a video, and so this let's make this color. Actually, I'll make it a blue color, and then actually there's blue and red. So let's see, there's blue, and then there's red. You know, okay. So what this is over here on the upper right, this is not a mirror. This is a grating now. And so then we take this here and we draw this little line. We go like this. Now all the mirrors are tunable. That's, you know, the other one is tunable, like, you know, we can adjust that too, but that's more for alignment. Now this one here, let me think about this now. Okay, so what I need to do is I need to go back here, and then we gotta Now what happens is, okay, so there's another arrow. It's very difficult to kind of show you. But so when this turns, okay, so what happens is we can actually do a straight line here with that size. Uh-oh, is that not the right size? There's that one. There's blue. Really can't see the colors that well. You can't really see the colors that well, but anyway, what the fuck. So, what happens... Oh, wait, now let me think about this. That's going to make... so that means the top... In order for me to turn this, that means the top ones... that one corner on the left is frozen, and the one on the top towards me and the one on the bottom towards me are moved such that the mirror moves the spectrum back and forth across the prism. So there's a spectrum adjust, which is the top adjusts towards me and the one on the bottom, and then there's an alignment adjust. So I think once it's lined up, it's going to skew unless both of those adjustments were tied together in one uniform motion. I've got gears. If I use a gear and have the gears turning in such a way that they move in unison, maybe I could do something like that on the end. And so what happened, what I was looking at is this video, and because the color, because what I want to do, and it's actually going to affect that beam at the bottom as well. Okay, that one at the top. That's going to go across. It's going to go down to the bottom one. That'll make that one go across. It should make it go across when it goes to the tube. But the one, that beam's going to go straight down to the bottom beam splitter, and it's going to go across like back and forth towards the page. Okay. But the one in the middle, is going to be skewed incorrectly. That's going to have an adjustment on it. Whatever goes through that middle beam splitter, it doesn't matter what the bottom beam splitter sees, because whatever the bottom beam splitter sees, it doesn't matter what's going through that middle one. What matters is going through the middle one is the one that's down in the back of the cylinder thing. No big deal. I think that's going to work, but that means that's going to require adjustment for that other beam splitter too, isn't it? Right now, it's really not into the picture. This is a future. Once the basic interferometer is done, the addition of this sideways interference beam is going to be added. Cool beans, huh? So at first, well, I was thinking, these slits need to be adjustable. They were moving the grating. Now that slit's going to be at a 45-degree angle. The slit in the picture that I saw was completely parallel. No, wait just a minute, because the beam coming down is going to be perpendicular to the slit. Slit's actually going to be oriented different. It's not going to be like that. It's going to be like facing the page or whatever it's supposed to be, in order to get a single color going through the prism at the bottom. And as far as filters, I don't really know. That's all I want to talk about, is the addition of those slits. Slit at the light source, and what that does, it allows you to pick off a certain section of the grating. But my initial intention is to have that wide open, so that so maybe both of those could be variable slits. Let's see. Let me just do this here. I want to just type in wide open 2. And then we got that, probably. Let's make this here, and then we'll just do like this here. Yeah. I know what's happening with, well, I should probably put the arrow there. I'm just gonna put 2 arrows. Possible. How would I move the slit? I'd have to have a way to control the movement of the slit between that beam split or whatever. I bought a slide with this, I don't know, it's got this film type of stuff in it that has slits on it, and I don't know what the temperature thing of that thing is, whether that's going to cause an issue. Something I didn't think about, because I'm making this room cold. So let's save this as, it's going to be number 2. Interferometer 2. what the slit does is I don't know why why they put two slits in there. But what it does is so if you look through a basic interferometer, you just see all the colors like red, green, blue, and yellow, whatever. So what the slit does is if you look at something like a fluorescent light or something like that that's got certain intensities of certain colors, you won't see them unless you use a slit. So what the slit does is that it allows lines of interference to get accentuated, or I don't really know. It just shows, because I got this other little spectrometer thing, and it's got a little slit thing on the front of it, and I can look through it and see the light, and if I look off to the side I can see the spectrum. And with that slit, I finally got the slit adjusted on it, and I could see lines. There were lines there in the blue and yellow and red and stuff, and it was coming off that fluorescent light. I got other colors of light, and I also have filters. I got a filter pack and stuff like that. There's things to mess around with. But the whole idea is to get this mirror, this interferometer setup built onto this platform. All I gotta do is build the support. I got the support beams. I got the idea now to support the threaded rods with the spring setup. There's two on each end, and they're outside of the mirror setup. They're on the mirror support thing. And the spring, adjustments are outside of the width of the mirror holder, like a really small amount, so that's good. And then the support is like on the outside of the mirror holder, and the rod is here, and there'll be a hole drilled through the support just wide enough to let the 440 screw through to be able to tune that rod. Now, what's good about this, I think, and I don't really know yet, the face of this here, the face of this piece of plastic here, it's really, really smooth. It's very smooth. So I don't really have a screw enough in front of me, but I suppose if this, you have this, I got a rod. So if you, this is a smooth end, I can tell, and this is a rough end back here. Just mess with the rough end part. I mean, that's not gonna really matter. But if you take the screw, this is a larger one, and you put it up against this piece of plastic. And so if you turn it, that's fine. But the other thing is, what if there's a vibration, okay? Now, if there's any kind of vibration, it might be something like this. Or what if there's a big vibration and this part comes off, and then this is actually gonna be on the bottom. So if it should come off, that part is gonna swing back over like so. Then it's not gonna be, I think at the start, there is going to be some pressure, but at the start there's going to be no pressure. So the screw sitting here, it's got an eighth of an inch of play. So then it goes in, and any vibration, because this is not physically connected, it's going to go up and down like this. It's going to revert back to its original, and then if it has to be, fringe will spread out all over the whole picture, so I don't want that. Maybe there's got to be a way to measure vibration, I think. I thought about doing it. In fact, that's on that picture right there. I was going to add a beam splitter there in the behind of the tuning cavity. That goes down to another mirror, which bounces off to a vibration mirror, and that goes in and goes through the wall and goes to a sensor. The worst vibration would be up and down. So I don't think there would be enough. I mean, there's really not a lot of space where I got that screw, but the screw's smaller than this. And honestly, you know, I mean, that would be, but the springs are they're not strong. The springs that hold this on are going to be weaker than the ones that are holding the rod in. The rod's going to be pretty stiff. This is going to be like, it's going to be like this kind of type of thing. So there is a potential for that to come across and slip back over. I don't think the way I have my setup, and then the actual case itself, when I put the case down, that's actually going to be sitting on spring and rubber support as well. So really, and then once it gets set up, I'm actually going to pound on the floor and stuff and hit things and find out, while this is at rest and this is up against this, I want to find out if it slips off altogether or exactly, you know. And then for the other beam splitter, this is going to be held like this, so this is going to be held down with gravity. So that one's going to go up and down. So that one's definitely not going to come off. That's going to go up and down. So that one's not a problem, but the one that's a problem is the one on the side, because this is going to go up and down like this. The 440 screw is permanent, and the rod, the container rod, is on a spring. This is on a spring, and so that's going to go up and down like that. Maybe I could put something on the bottom. Let me think. The piece that I've got that I'm using, it doesn't have that. It's just flat and small. I don't think it's, that's a lot of vibration, but if it's on springs, who knows, right? Who knows? Who knows these things? So the objects under test that I'm using, they're solid objects, and they produce anywhere from a singular to multiple lines of interference and constructive and destructive interference. When it goes to the tuning cavity, I have no idea what's going to happen. So let's say that I discover some information on a certain color, like it's going to show up. If I use the slits, I think that the slits causes the lines to show up. If you don't use the slit, you won't see this line. But the only problem with that is you don't know if the information is coming across a color that's not on the line of the wavelength of the object under test. Then you're kind of defeating the purpose. Why even bother having the slit in there? But what happens, I think, is the slit is, maybe you you start out with not using it, and then you see information, and then you say, okay, well, this information is coming, I see more of it on the yellow. Okay, so now you can tune this. You can put the slit back in, and you can tune this to that color, that where that information is. And let me think. And what that will do is not going to add power to the color. It's going to take away noise, is what it's going to do. It's going to make it quieter around that region. And then, let me think. You can add the filters on each side, which makes it even more quieter. And so you're using a mechanical setup to increase the signal to noise ratio, which I think it's detrimental. At first I was thinking, I wasn't even thinking, I was thinking you move the grading and the color, but you'd have to move it, you move the grading and the color goes back and forth, but still it's not narrow, it's more of a wider range, right? So what if it's like yellow, and you still got all the color on either side of yellow that's going in there, and if you use the slit, you can narrow that down. You can narrow it down, and it'll show you, but I don't think that's going to work, because when you use the slit, you're going to see the colors of the object under test, and the information may not be coming in on one of those objects under test. So even still, you can still use the slit, and you can go over to where that noise is, and it's not that's the key. It's not necessarily where the lines are going to be, but the slit allows you to focus on that area, even though, I don't know. That's just it's a trial and error thing. What are you gonna do, right? All right, so that takes care of that idea. The addition of slits in those places right there, the light source, and maybe the second one could go in halfway between a beam splitter and the grating, or actually I think it's closer to the. No, wait. It's actually closer to the beam splitter. I don't know why they put it there. I'm just thinking, like, if I have a grating, and I have a mirror and a light source that's 90 degrees to the grating, I can test it. I can test the slit idea. I still have not made I gotta fabricate a container for the slits. I've got razor blades to do that, and I think there's a way to sharpen those, supposedly using a pair of jeans. There's that, and I also have the cards, which are much narrower. I don't know what temperature is going to do with those cards and the slits that I got. So there's that. I think it seems like I could put the cards inside of the case, and then try to figure out. So once the whole thing is built, I got this platform, and everything is going to be built. The mirrors and everything's going to be on a movable platform. So then now, instead of having this case sitting here, I'm going to have this platform, and then I'm going to have nothing to support the light, so I'll have to have like a support for the light that comes up. I can set it on the platform and then run that into that mirror, that grating, and then I can coarse tune the grating, and then I can put the slit in there, make the platform for the slit. Yeah, maybe that's what I gotta do, because I don't know how that slit thing is gonna. That's just gonna be sitting there like this, but it has to have a movement. Like it's gotta have a really fine that was a nice discussion, huh? I got a lot of that, right? What else? My next, so I gotta build the supports. I got the plastic for the supports. I gotta cut those up, build them, and then like I'm working tomorrow night again, and I just don't know. I might be able to at least cut the supports if the weather's good tomorrow morning. That's that plan. Okay, I got two power supplies that I've got to check. I know how to do that, and I want to do that on the stream. So maybe I don't think maybe tomorrow night. Maybe I can go out and check the power supplies. What else? I've got a bunch of variable resistors. I needed to have like a mega ohm resistor. I got all the components, and then I've decided the comparator that's going to be used. Oh wait, backtrack on that. So you have this light beam coming in, and you have these morons, these idiotic morons that know absolutely nothing about life, come in and try to send messages to your stream, and you know, that kind of thing. And so you just catch them in the act and you get rid of them, just like that. So power supplies need to be checked for accuracy and ripple across the power supply line. And I also picked up some 9-volt batteries. So now I've got a pair of 9-volt batteries that I can use. I still have to have, I want to have some good regulation, but maybe I don't really need it, you know, because there's going to be like two signals that come in. One is going to have the carrier, one is going to have the carrier plus the noise. And so, in order to change the phase to get rid of the carrier that's got the noise, is that picture that's on there. You see, I've got this noise comparator in here, right? Well, there's another way to get rid of the carrier, and it's not using this setup. Is because what happens is that the mirror number 2 is moved ever so slightly, and what that does is it changes the phase of that light beam, and it goes into the destructive mode. The destructive mode is actually it's getting rid of, it's taking those two beams and putting them out of phase, so that all that's left is the information that's coming across the light beam. Oh yeah, this is the secret to a heterodyne Lightwave receiver. But yeah, it's like this implies that okay, so what happens is that you have this source of energy, and in order for the energy to make it onto this plane of existence, it has to interact with something. And so what I do is I take, number one, I take the light beam, I shine the light beam on some material, and so the light beam carries light, and so when the light interacts with this material, the interaction of the light and the material creates a noise effect, right? And so different types of material create different types of noise effects, and so then this noise effects, they go into the tuning cavity, which I don't know if it's going to work. We'll make an assumption that it works. If it doesn't, really doesn't matter. So let's say that the noise effect is happening, and now you've got this light beam that's interacting and it's creating this noise, and now the entities from these other dimensions, they can see that information through this portal of infinity that exists exists when this noise is created. And so you can do things with the light in order to change the effect of the noise. You can do other things to change the effect of the noise. And this is all mechanical. And so when you change these things, you monitor the output, the electrical output, and see if there's any rise in the signal. You're looking for some stuff that's happening that's really not supposed to be there, and it may happen at certain wavelengths, or it may happen, if you turn the object under test just right, it may cause certain things to happen, and all of this adjustment, it's within like microns. It's just ever so small, and they said like if the light beam was tens of meters long, you'd have light interference. But if it's in a small case like this, the chances of air interference should be like small, that you wouldn't be able to see it. Hopefully, I don't know. We need noise. Noise needs to be part of the system. And that noise is, once it's created, it can be manipulated. Now, the light beams supposedly have both electrical and magnetic properties. And so my feeling is that the light beam interaction is going to be on the magnetic side. And so if we use a polarizer and get rid of the electrical, we should see the magnetic. The magnetic goes through, and it's still part of the light beam. Some of the electric's going to go through, and all of the magnetic's going to go through. So then I have I've got some ideas about what I'm going to do with that magnetic signal. And I've got right up here, I don't know if you can see this or not. I don't know if this is the one that I fixed. This is as you can see, is a very large coil of wire, and the wire itself, it's thinner than a piece of thread. Okay, you will not be able to see it, I don't think. It's like right there. Okay, it's like thinner than a piece of thread. And so this thing is heavy. So what I want to do, unfortunately, the other end of this is buried down in the bottom of this thing. And so this is going to have to get put on a spindle. And I've got to do some calculations on magnetic detection using coils, rather than using a Hall effect. Don't really know yet. If the magnetic wave, it's flat like this, and so it travels this way, but it's oriented this way, so it's going back and forth on a plane like this. It's not flying on a plane, but so it's going like this, and it's flat, and it's traveling through time. So normally, I don't know, well, actually it's really not flat, because the electrical beam comes up in a spiral like this. So that implies that the magnetic beam is also in a spiral. It's also circularly polarized. So, and it's traveling really fast, so the spiral's like really quick. And so it's traveling, it's going in a certain direction. And so if the coil has to be tuned to that magnetic frequency or whatever, you know, maybe I can pick something off from that. I don't know. Let's see. Because the other part, the electrical part, when it comes off the detector, let me think about this for a minute, because I think the detector is only going to collect the electrical portion of the wave, and the magnetic portion of the wave is just going to go right through the detector. It's not going to pick it up. Maybe there's, let's see, like, if I knew what the level, well, okay, so if I know what the level of intensity of the electric portion of the light wave is going to be, and then I take 1% of that level, and then I use that as a reference for the magnetic strength, and then I can plug that number into the formula, which is converts the magnetic strength into current, which is it's a B formula, I think. Let me see here. Probably look at it here. Let's see. I think it goes to current, not voltage. Let's see here. Magnetic field strength depends on the current. First, facing long straight line, magnetic field falls off. This is proportional to current. B equals parentheses UO, which is permeability divided by 2 pi r minus L, with R being the distance from the wire. So if you increase the current, the magnetic field strength gets stronger, but if you move farther away, it gets weaker, yada yada yada. The magnetic field strength generated by a current carrying wires are clearly so we know the magnetic strength, and what we're trying to determine is the current. So if we make and the current is in amperes. Let me think here. It's multiplied by 2 pi r divided by the permeability. If the permeability so air is 1.25, it's 10 to the minus 4. So that's 6 now. So 1.25, 2.6.3. So iron has a larger permeability, which is it's a larger number, but that larger number is on the bottom. So if it's like, it needs to be a smaller number. Was times 2 pi r equals mu o over I. So mu o is on the bottom. Mu o is the permeability of free space, which is 10 to the minus 7. Let's see, where it's very long. Magnetic field depends only on the distance from the wire. The distance from the wire r, not the position along the wire. So if r is big, magnetic field strength depends on the distance from the wire. R, that's the radius. Long straight wire. We're talking about a coil though. Magnetic field strength by a current carrying circular loop. Lead to the center of the loop. It's still divided by mu o. So I don't understand that, because if mu o is a larger number on the bottom of the magnetic field strength, the current's going to be lower. One way to get a larger field is to have n loops. Then the field is bn. Note that the larger the loop, the smaller the field at its center, because the current is farther away. The number of loops per unit length of solenoid, n equals n divided by L, which is a large number, n being the number of loops. Say it's like 1,000 divided by a length, etc. B field strength anywhere, uniform region of the interior, not just at the center. Large uniform field spread over a large volume of possible solenoids. Yada yada yada. So you tune these coils. If you have a capacitor and you tune the coil, you can tune it to maybe some frequencies that it's going through the coil to amplify, like have the preamp, like you have a coil. It's sort of like a tuning thing in front of a radio. Maybe it's part of that. Here, if R is large, the current is large radius. Magnetic field in the center of the loop is thus R is the radius of the loop. Yeah, I don't want a large coil. It's just weird though, because that number on the bottom of, oh wait, it's relative permeability. U is divided by UO. So concrete, which is similar to air. So if this number is smaller, no, that number is big. It's 350 to 500. Ferrite goes up into a really large number. Has to be an air coil. You want the smallest number you can get. I don't know, it's crazy. Water is 0.9, vacuum is 1. Air is 1 times 10 to the minus 6, but the relative permeability, this is U, which is H divided H divided by meters. All values say room temperatures. Values for the materials on Henry's per meter. They're saying mu O. I think it's an air coil. It's got to be an air coil to get the most current. See, we're detecting a magnetic field, so we're creating a magnetic field. We have a magnetic field that's being created, and it's a changing magnetic field that's going through those wires. And so, if that's a small number, and the number on the bottom is large, here it's just 1. But this is mu over. That formula is mu O. What the hell is going on here? Current is divided by mu O. Why are they using this? Must be for an air coil then. This is just a wire. And this is that's the long straight wire. And this one. Times 10 to the minus 5 Tesla. So B is due to the wires taken to be 1 times 10 to the 4 minus Tesla. The equation thus can be used to find I. Moderate large current produces a magnetic field at a distance of 5 centimeters. Well, if you use a large number of turns, it's going to make it more sensitive, you know? But I think it has to be long straight wire. If that number is longer. Magnetic field strength produced by a long straight wire current is found by experiment to be such. R is the shortest distance to the wire. It's turns per meter. Turns per meter is the current. Get a large number of turns per the length that increases the current. The wires, the total amount of current crossing the surface bounded by something. There it is. The integral consists of the segments it's shown. Note that the red is the current divided by the length is equal to the sums per units of henries. To increase magnetic field, you can either use more turns per unit length or increase the current. More turns per unit length. Magnetic field is uniform inside the coil at the magnetic field on the axis equal to magnetic field close to the cylinder wall. This does not apply close to the ends of the coil since we have a differential field. Why am I seeing the same picture here? Let's take a look at this one here. You want the currents in the coils to flow in the same direction so the magnetic fields of the two coils add in the space between the coils. Magnetic field sensor. Wow, okay, that's kind of I was thinking of building something, but this comparison, this phase thing, has to do with the mirrors and not electronics. Because I solved that problem. Yeah, I don't know what's going on here with this. This is weird. I mean, I could see increasing the number of turns is going to make it more sensitive. And it just seems like it would have to be a lot of turns with a very, very small open center. That just seems to me like what it should be. But I'm wondering, you know, let's see. Effects of coil. More turns in a pickup coil increase inductance and DC resistance, which lowers the resonant frequency and can make the pickup sound darker and less sensitive to high frequencies. That's interesting because we're probably looking at high frequencies and let's see. Well, a wider coil shape can sense a broader string area but does not always guarantee a fatter tone. It's going to increase the resistance. Inductance increase. More turns in a pickup coil increases inductance, which is L. Also reduces resonant frequency. Increase in inductance lowers the resonant frequency. A longer coil can affect the overall sensitivity, but is not solely dependent on its length. A wider coil shape can sense broader area of the string, but does not guarantee increased sensitivity. Resonance, huh? See, this noise that's riding on a light wave, so it could be anywhere from audio all the way up to 12 gigahertz, you know. Um, how do more turns in a pickup affect the sensitivity? I am trying to figure something out with these stupid coils. RF coil, gradient coil, RF electronics. Simple RF loop coil. LC circuit tuned to certain resonant frequencies. 60 coils and digress added in parallel. In order to tune the coil for frequency, pin diode. Ohms into a single loop coil. That doesn't make any sense. Field strength. Optimum coil radius. Field strength. 20 millimeter. In millimeters. 20 millimeters. R sample greater than the resistance of R coil. A Q ratio greater than 2. They're using symbol. I don't know what this is. Adaptive RF coil. They must be using a lot of current or something. They're talking about this MRI, but I can't get the information I'm looking for. You know what I mean, Jelly Bean? That's not going to help me. How wireless charger automatically detect RX coil to turn on. Wireless chargers. That's an interesting looking coil shape. Magnetic field detector circuit. Let's see. Simple Tesla coil using a 2N222. Here we go. 300 turns in a secondary. Where's the primary? The hell? There's a primary coil with 2 turns. Cable generating high voltage. Demonstrate. This article explains how to build a simple and compact Tesla coil. This is cute. The Tesla coil uses self-oscillating feedback system, power supply switching, yada yada yada. Power flows to 20 kΩ resistor, etc. Oscillating. Primary coil 3 turns directly connected to the collector. Secondary coil placed in proximity following magnetic coupling. High frequency, high voltage AC signal in a second. This can light up fluorescent bulbs. Yada yada. Oh, I don't know. I don't think it can be a long coil. It just seems like it's got to be. I think there's a limit. I think there's this, like, if it goes too. If it's too far away, if the center of the coil is too far away from the center, it's going to lose information. If it's longer, like this, then you're going to lose information because all this information going through here, and it's going through time. It goes through this way. The magnetic field, though, is actually flat. I mean, assuming it was up and down like this, if it was up like this, like an AC sine wave. I wonder if the coil has to be aligned different. Magnetic field due to Himmel's coils. Yeah, that's nice. Metal detector. What's this here? 15 gigahertz quad core VCO with extended circular coil. VCO buffer, inductor frame. Circular geometry of a quad core VCO. But these coils are like really, really small. 12 gigahertz spectrum usage rules change without re-auctioning it. Many argue they're talking about 5G use wouldn't 5G 12 gigahertz. What the hell is this? 5G using 12 gigahertz. But still, that's not going to be. That's what I would call a channel in the light on the light beam to detect. So I'm making a rash assumption about the type of information coming across a light beam. It just seems like it wouldn't be audio, it would be more on a higher frequency. But if I use, well, the detector picks the signal up, it turns it into an electrical signal, like a radio station. So I use a 12 gigahertz. That's what the other picture was. This is an SMT. I have something, but I was thinking more along the lines of a receiver, not a transmitter. A direct conversion receiver. Design 12 grams ultra phenols. Phase lock loop. Reference. Max 2880. That's ridiculous, man. They want this 12 gigahertz, this little kit, for like $430. That's ridiculous. This is from Analog? It's a data sheet. Hardware. Yeah, well, there's a circuit there. Oh, that's a lot of crap. Yeah, you can build something a lot easier than they just. This shit's getting really complicated. It's like getting out of hand, you know. Uh, to pick off something at 12 gigahertz, it's like a smaller scalar SMT type stuff here. There's something here. Millimeter wave. HF, VHF, UHF. Converter. And it's all in Japanese. I wonder what that SMT thing is I got. One gigahertz, 2 gigahertz, Type C USB. Oh wait, you know what? I just thought of something. My my SDRs. I think one of my SDRs goes up to 1 gigahertz. Anyway, just a minute. I got two of them things. We're supposed to work on this SDR business, and we have not done so. So damn 1.8 gigahertz. Well, that's interesting. I'm downloading a DVB-T driver and software, which connecting the RTL SDR dongle with the original DVB drivers, we were able to receive transmitted stream. Let me just copy this because this is information regarding this. Is that still on there? We could probably just get rid of that for now. And then go to my project thing here. I wasn't thinking about using the SDR as a receiver. Off of the Lightwave signal. There's a program, it's called AirSpy SDR. And it says you can purchase it, but, you know about that plan, right? Modify power sample, modify PLL circuit for better stability at 1.5 gigahertz. It's a DVB-T tuner, rtl.sdr.com. This is what I have, but I don't know that much about it. Fake RTL SDR B-log clones. Slightly curved enclosure. Website URL on body. Well, I found out what that is. B-log brand. I have no idea what it is. Well, I can't be messing around with this all night long. This has an antenna. And then it has, it's slightly curved. I don't know. This is NSY. program this thing with various types of software. So, see, if I use... this thing is just kind of sticking out. If I use a transistor, let's say I've got this noise coming in off of this light beam, and the noise that I'm seeing is up in the gigahertz range rather than audio, which really, when you think about it, makes a lot more sense. This is the RSP1A. Alright, so let's see here. RSP1A. SDR play. Okay, so this one goes up to 2 gigahertz. A massive 10 megahertz visible bandwidth. What is the 1 kilohertz to 2 gigahertz? But what about discontinued production in 2023, superseded by which can be found here? That one's $133. I paid $100 for mine. That's 1 kilohertz to 2 gigahertz. Yada yada yada. SDR to play downloads. I got a lot of that stuff. It goes up to 2 gigahertz. But what about crap. Let's go for images. What's this here? First 10 minutes of use, not bad. Setup was okay. I chose to use HD SDR, etc. Let's grab this little thing here. I'll just make a copy of that. Everyone needed to push LNA all the way up, which turned out to be up towards 0. Speaking of which, not the personal. Here's an audio file from KL model Alaska with a relatively strong signal. Also set up with USB, etc. 340 meter long antenna. Let me think about this. Okay, so you've got a video detector. No, the video detector spans multiples of 12 megahertz channels. You know, this is interesting. I don't even know why. Because I was going to was going to go from the detector to a preamp, and the preamp was the 2N2819. And if I go this is interesting, you know? This is really, really interesting. 3819. Two N 30 shit 3819. Operating up to 450 megahertz, an RF amplifier. Oh shit. Am I using this for that? RSP1A. RSP1A. Input sensitivity. Specifications. RF. Download. Oh, screw you. The fuck? 50 ohm antenna impedance. 50 ohms. The fuck? I can't put 50 ohms on that signal. Oh my effing god with this stupid ass fucking whatever that shit is. Let's do here. Let's try this one. Not. Okay, what's this here? Let's grab this. I'm just grabbing a bunch of stuff for this rig here. It's funny how things go into certain things, you know? Hmm. something here. Up to 16 individual receivers in any 10 megahertz slice of spectrum. Powers over the USB cable USB socket. One antenna input. Additional software selectable. High Z input for up to 30 megahertz. Filters. Dual tuner. Robust connection. Overall performance. Noise figures. 5 dB at 1500 megahertz. Continuous coverage. 50 ohm. IF bandwidths. There's a bunch of those. Temperature stability. Filter. Maximum input power 0 dBm. Well, it's going to be low, very low anyway. Gain and noise figure versus LNA setting at 100 megahertz. Noise figure is the green one. LNA setting. Selectable filter element rejection greater than 140 dB. That's pretty good. 50 ohms. I've got an SMT amplifier. And I think it's a broadband amplifier. This is really weird because I would have to build. You got the detector. Let me see something here. This is an LT1028. Yeah, but this is a... Yeah, this is not what I want. See, these people are not even thinking in terms of 12 megahertz. Well, that thing only goes up to. That would be like one channel off of a 12 megahertz. I mean, a 12 gigahertz channel. It'd be like. I don't know why that. You know what? As a matter of fact. As a matter of fact. Look at all this shit I got here. This box right here has my SMT stuff. Oh shit, that's oh, I didn't even know I had those in there, and that's upside down. Fuck. This isn't SMT. Okay, let's just hold the fort here because we're gonna look something up. OPA 604. This is an FET audio operational amplifier. OPA 124. Obsolete. I've got something else. Oh shit. What time is it? Well, it said something about. This is an audio amplifier. It's a very sensitive audio amplifier, I think. Yeah, this is just crazy. You know what? This isn't not what I'm looking for. I don't think it's in here. I got some photo detectors in here. Yep, this is definitely not. Oh boy. I've got some I got some SMT stuff in static sensitive bags. Let's try this here. No, that's not what I want. It's not that difficult to build it. God, they want $10,000, $14,000 for the. Well, that's a 50 watt. I don't need a 50-watt freaking transmitter, you know. It's an LNA. 2,400. What the hell is that? I don't even know what that is. That's 2.4 gigahertz. RF amplifier 20 watts on Japers Craper. Well, I got the thing. Power detector. Um, RF power splitter. 500 megahertz to 4 gigahertz. For 99 cents. You know what? Nine to 12 volts, 30 dB low noise LNA broadband module, 0.1 100 kilohertz to 2 gigahertz amp module. For $13, you get two of them, and there's only one left in stock. Oh, is a 20 dB gain. That was a 30 dB gain low noise amplifier. And it's already built. Like, I could use that design and use it build that one that they got one showing here. Looks like a plane. What the fuck? Ah, shit. Dummy load. 10 kilohertz to 6 gigahertz signal boost, etc. Yada yada. 20 dB. 10 megahertz. 10 megahertz. 10 megahertz. 0 hertz to 12 gigahertz. 500 ohm. What the hell is that shit? Well, that was interesting, wasn't it? RF gain amplifier. It shows the IC, it shows a resistor, it shows your panel output, it shows, I think, a couple of resistors. I don't know what that thing is. It's really not that much to it. 30 dB of gain. The SMA connector. I should copy this here. Now I could probably look for that circuit. You know what? Let's try this here. Well, this is just a bunch of BS, isn't it? This is changing the idea for the detector. Instead of running the detector, or I could have like the 3819 goes up to 450 megahertz. Is that what I said? It doesn't even tell you. What's this one here? I don't even know what the fuck that is. Huh. Max drain source on state resistance 300 ohms. Yeah, but that's just can't find what I'm looking for. Why don't they give me this freaking information? Okay, here, mid to high frequency features low noise leakage, guarantees high gain at 100 megahertz. Excellent high gain, 11 dB at 400 megahertz. That's pretty good. That's pretty darn good. AV60 at 100 microamps, very low distortion. So I could theoretically use this as a preamp with a low impedance output, and then connect that to the SDR. Then I would only be looking at 0 to 400 or 500 megahertz if there was something in that area. What I'd want to do is I'd want to connect the SDR to this other preamp, which I don't seem to see it. And I'm just looking. I'm looking for a basic circuit for it. It's really simple. Snaplink RF amplifier. Because I don't know the name of the one I got. And a lot of the stuff with SMA, you design the capacitance inductance using the SMA circuit. I'd have to go into it, wouldn't I? What's this thing here? Oh, what's this here? 0.025 gigahertz to 12 gigahertz. What is that? Gigahertz? 25 megahertz? That's got good frequency range. Frequency in gigahertz. Yeah, this is different from what I got. This is like a RF in, it's got RF bias. The thing that I got is only a transistor. I don't know if I can get this for free, though. Hmm. Usually you gotta buy this stuff in multiples, you know? Sample and buy. Price per unit. Price per unit. Lead time of 10 weeks. One of those is $80. Yeah, I don't think so. I'll just find the one I got. It's just an amplifier. It's not this confusing ass BS crap here. I'm just gonna get rid of all this shit. I just dump all of this, right? Sorry about that long ass discussion over pretty much nothing. Hello. Alright. I think it's time for me to call it quits. But I figured out something. So wait just a minute now. Wait a minute. Let me look at something else. Let's try something else here. I don't think you can use that with an Ellen. No, wait just a minute now. Photodiode. Photodiode. Yeah, it's going to get rid of that. Oh boy, let's see here. I know this is not going to work. 5 microseconds. 5 volts per microsecond. 1 nanovolts per microhertz. Gain bandwidth product. Jesus. I don't know what I'm doing. $180 megahertz? No. Yeah, see, I don't think I'm going to find this. So, it has a detection and it has a current, but let's see. Probably input. Usually those things have high input and low input impedance. The RF port signal lines RF port should have 50 ohms impedance. These are 50 ohm. I'll bet you. That SDR is 50 ohm. So that means okay, let me just look at this again real quick. I forgot I had those in there. Photodiode, yada yada. Internal, no, it's feedback. Please don't give you some good information right up front. Like, what the hell, you know? No, wait. This would be... Jesus. This just helps me so much, you know? I'm never gonna get there, am I? I've gotten some information that I wasn't planning on looking for, though. Holy shit. I got... They're saying these are like $10 a piece. Use circuit designer. They don't even tell you what the F the frickin' impedances are. Dark output 7.5 millivolts positive going. Where's this here? It doesn't help me. Okay, here they got something, but they're not telling me what the values are. R1 and C1. I can't get nothing. I can't find shit here. They're just connecting it direct to a freaking op amp. Like, I don't want to do that. I want to connect it to maybe a load resistor or something, you know? I need 50 ohms. I'm going to need... What's this here? Opt 101 input. Optic audio capture using laser reflected surface vibrations. This project demonstrates, high level design, concept, photodiode surface signal. $22? They want for that now? Are you kidding me? Man, everything is so expensive, you know? Holy shit. I got $100 worth of Opt 101s. Huh. What the hell? I think I only paid like $10 for them. Opt signal output. Jesus, what a freaking mess this is here. Well, it's an interesting little circuit, but it tells me nothing. Oh, I know nothing anyway. So this has a built-in operational amplifier. It's got a feedback circuit with and you can change things with a pull-up resistor, which is like in series with the 1 meg ohm feedback resistor. Whereas the other detector that I got, I think that's only a diode. It's a photodiode. This is like a photo op amp. That's what this is. It's got the detector and the op amp built into it. What's this here? This looks like the same circuit. And it's all in Japanese. Like, what the fuck? Okay, I got it translated. It does have... It's showing you how to connect this to the Arduino. It even gives you a code. Output D analog read. Analog. Arduino, breadboard, yada yada. It doesn't tell you. It doesn't tell you what the value of those stupid ass fucking chips are. R1C1. Oh, wait, R1C1? Yeah, that's the output. That's the option for the output feedback, but they put that in there though. R external, C external, R1, C1. Output. Huh. Where's the circuit drive? How the hell do you connect it to the Arduino? They show you. What is this? I can't even read this fucking picture. Save image. Let's put it here. What the hell? And this is I go to pictures and look for opt 101A LMP here. Why in the fucking hell are they showing you this stupid ass shit here? What the fuck? 5 volts to VCC. That's okay. AO goes to minus volt. That's from the Arduino to the item. 1 meg ohm to the minus volt, ground to minus COM. They're showing 1, 2, 3, 4, 5 cables. Oh, this is a little better picture. The ground, VCC, the output I think is a green cable. It doesn't tell you where the fuck it goes. I have no idea. No freaking clue whatsoever. Analog. There's an analog. Okay, when you go down to the thing here, it says output D equals analog read, yada, yada, yada. Huh. You know what? Why would I want to do that, though? This Arduino crap. Jesus. This is going to drive me crazy. Maybe there's another one here. Unexpected output range after trimming dark output voltage. I have connected RxD and 60 to change responsive bandwidth. Yada yada yada. Yada yada yada. I connected. Yada yada yada. Swix fan sync is my signal not saturated anymore due to the addition of the ambient light. However, it's now ranging between 4.4 volts as before the dark is now. It does. How does it go to negative voltage? Adjust R with no light. I didn't think I was going to be doing this all night. But then I'm thinking, I'm trying to come up with this plan for detecting at least 12 gigahertz off of that Lightwave, which I didn't even think I was going to do. What's this one here? That's a different one, ain't it? Here's the circuit board. It's all apart and everything. But they only charge you $1. And the thing's like $22 a piece for just the operational amplifier thingy. They don't tell you nothing, do they? Description, yada yada yada, pictures. Yeah, it's the same thing, but you gotta solder everything to the board. Yada yada. Why do they give you so many pictures of the same thing? God almighty. What's this one here? Up 101, up facing up 101, 5 to ADC, analog to digital converter. So it's just an analog output, but it doesn't tell you. Well, if it's an op amp, then it must be. You can't load those. It's got to have a high impedance to a low impedance output. I wonder what the. Let's see here. I'm coming up with an idea. fucking AI. I spent 2 hours basically trying to figure something out with just 2 transistors. Drain to source, 20 milliamps. Output conductance, output capacitance, picofarad. I'm not gonna find it, I swear to God. Let's do... I could do the circuit program test. I'm not gonna do it tonight, but come on, what the hell is wrong with you? God, this is so fucking slow. What the fuck? I just lose my internet or what? Oh, that would help, wouldn't it? Alright, here we go. We're getting somewhere now. That's 5K. That just shows a capacitor. So, in other words, I'm thinking up 101 into the 3819. This is another circuit. I already got some diodes, but this is a different setup. The up 101 goes up to... What does it go up to? I can't even remember. Did I put it on there? Probably not. There's an up 202. Why is that in there? Oh, so that covers the light range, which covers those bandwidths. So it's just the output impedance. Why wouldn't they tell you? Voltage output. Finally. Well, this one says a 10K load. Okay, so 10K into the 3819. That's definitely not a problem, I don't think. Okay, then we go back to 3819, and it shows a capacitor into the 3819 capacitor output, but the frequency range, I think it has a low output impedance. Let's see. I can't find anything though. Alright, so this is the one that goes up to 400 megahertz. And the up 101, okay, so that's not a problem. So this goes up to 450 megahertz. And then, let's see here. It's this output impedance of the 3819. Well, this one, let's see what we got here. Maybe we can find something. What they call it, a MOSFET. It's not a MOSFET, it's a JFET. What's this here? Maybe we get lucky here. This is an R load, a load line. R load of 100K. Thought you could put a bigger load on that. Yeah, screw you. You want to get my information, you know what you can do. What's this here? What is this? This looks like a timer. This output's going into a timer circuit. Well, let's do this then. Let's see. Wait, maybe I've got it in my directory. Transition frequency. That's just a lot to learn. Well, this one here has a 450 ohm output. Oh, that's some kind of a probe thing. Probe. I can't find output impedances for shit, you know? Well, the 21222 goes up to 250 megahertz. You know, I'm thinking around 100 megahertz. That's that's a start, right? So that's something. I think that would give me a better, because if originally I was just thinking audio coming off of this Lightwave, but if we can get up into the 100 megahertz, my scopes only go up to 20. That could be used to feed the SDR, but then I'm only up to like 2 or 300 megahertz or something. And anything above that's not going to be there. Then I could put the SDR in somewhere, somehow. But it's 50 ohms, 50 ohm output. So if the SDR is 50 ohms coming into the antenna, and you put a high impedance on it, well, the high impedance output's gonna see 50 ohms and it's gonna load the circuit. It's gonna load that output circuit. It really needs a 2 gigahertz preamp in front of it. Is what it needs, and I think I got that. And that way, I could have like a buffer in there, you know, to protect the radio. Floating base. I don't know what the hell this crap is here. I don't know what I'm looking at. Huh, I don't know. You know, the only thing I'm going to be able, the only thing I can do is just make the circuits with the circuit program. Maybe the circuit program will tell me. Because I give up. I can't find what I'm looking for. And I don't even know if I can do that right off the top of my head either. Let's see. Maybe I can just throw it up in here, huh? Wait, don't I? Isn't there a file that I have on here? God, I don't know. I just trashed all of that stuff, didn't I? Okay, so we've got, what the hell is VBB? Minus 3.5 volts. Wait, this is, something different. Test circuit for switching times. Probe. noise under test. This is gonna be down and dirty, ain't it, huh? you have to do this bullshit. This is bullshit. And believe me, I don't want to do this. Like, at this time and oh my god, come on. Alright, we got optical devices in here. Optical sensor, photodiode. I'm not gonna get into that. I think I made a boo-boo here. What the hell is going on here? Don't you do the sine wave thing on here? Where the hell is that at? Controlled. Frequency to voltage, voltage control, oscillator, transducer. I don't know how to use this program yet. Transmission line, user defined, voltage control, oscillator. I don't want that. Instruments, signal generator, that's what I want. A signal generator going into here, and then I'm just putting in something's wrong here. Man, you gotta have fucking good eyesight for this stupid ass fucking program. You can make the circuit bigger. Let's see. Let's save this as 2N amp 1. Where's the... Wait, I gotta save this file. Save. Simulation analysis setup. AC. Okay, we got a circuit here. Okay, what is this thing putting out? Wait, this is not good. This is a 1 volt peak to peak. Let's stop this here. Let's change this to 1 millivolt. Let's change. This is not amplifying. Let's change this to a 10. Change that to a 10. Something's not right here. The transistor's probably not getting biased correctly. Alright, so I got 1 millivolt coming out. Oh god, it's 3 millivolts on the base. What the fuck? There's something wrong here. How's that possible? Oh, we've got 6 volts here. Okay. This is amplifying. Okay, the load's pulling it down. Let's see. Let's stop this here. And we'll change this to 1K. Yeah, something's not right. I don't know if that's the it wouldn't be that capacitor because, you know what I'm saying? Oh, does that even look like it's connected? Wait, this is sitting on 3 volts here. Oh, I see what's wrong. Let's see. Let's add, let's see. Let's see if that helps. that's working. How the hell is it up there, though? It's not amplifying. I think the bias is wrong. It's 3 volts. Here it's sitting at 3.035 volts. Yeah, there's bias there, or the output's down here. But that's a lower output. Cute, huh? I'll have to work on this and call it a night. The whole idea, I guess, is so I was going to use a 2819, and then I was going to use a 2N22, and then, so like there's got to be, and then you go from, I was going to go from there to a speaker, or what was I going to, actually? An oscilloscope or something. I was going to tune. Do you have to add a, so that's where you add the frequency in then. You add the mixer into that receiver circuit, and then you tune across the band to get the signal. That's what you gotta do. I gotta add a mixer in there. Now that's what this SDR does. But if that input impedance is 50 ohms, that's going to be a problem. And it needs to be directly tied to the unit so that it doesn't pick up all this other crap that's out there. Yeah, I'll figure it out. Oh, what a night. I haven't watched a little bit of movie, go to bed. I gotta work again tomorrow. It's been an interesting little challenge. Yep, because I got a lot of stuff here. But I haven't been working with this electronic stuff for, oh my god, for so many years. It's just been sitting there. So 3819 to 2N222. That's a preamp. Another amplifier. And then, what was I planning on doing to measure that? I didn't even think about building a receiver circuit. Didn't even think about it. Like, I want this SDR to look at. Let me see here. Let me just try something else here. Let's see. buffer, emitter, follower. They don't help you at all with this shit, do they? Oh, here we go. The dude's got a circuit here. Almost like mine. He's got a 500 ohm. Oh, what the heck is he doing? Oh, yeah, that's the ground. He's looking at the emitter, which I don't typically do. 50 ohm. Oh, there's a circuit right here. Let's save this one here. I may have found something. What the fuck? Where's the stuff that I just hit on here? Well, this dude's got something here. What's this here? Link. I believe that the broadcast connectivity impedance antenna might be 50, and that you want you to add some inductors and capacitors for the antenna to make. However, this only helps if your wires have a characteristic impedance of 50 ohms. Now here they use a 3904. R1 and R2. R1 and R2. What the hell is that? Well, that's interesting. There's something here. I guess that's it. What's this here? Here's a common collector. The split voltage. No, that's not a split voltage supply. That's a 1K ohm load. Voltage follow is the safest and easiest transistor amplifier circuit to build. Piss off. Approximately has no voltage gain, but does have current gain. Common collector amplifier connected to a power supply. Understanding the circuit. All considered ground, yeah. Oh my god, with this stupid ass fucking ads. Alright, this is... What the hell is this here? BJT voltage follower circuit. Weird. This might help me though. Let's grab this one, I guess. I'm just having issues. I always have issues. Well, I really don't give a crap about MOSFETs now, do I? Holy shit, look at all this crap here. Wow. Somebody spent some time building something. This is all MOSFET shit. That one's not. There's little power transistors. Darlington pairs, yada yada yada. This is all MOSFET crap. Yeah, that's what this is. Buffer amplifiers. Oh, you got to be fucking kidding me. Well, let's try edge. Alright, what do we got here? This is a 3906. It's got some coils in here. This is a PNP. I don't like this type of a circuit. I don't even know what the hell this is. Transformer feedback buffer amplifier. Yeah, okay, that's nice. Oh, I guess that's a sign. I just dumped everything. Alright, I'm done. I got a few extra circuits. Maybe... Oh boy, I gotta look up. I'm gonna look for that SMT amp I got. Because I know for a fact that's 50 ohms. I know for a fact that's 50 ohms on the output. I even have a little case I can make, but the little board, you've got to do the etching in order to get the correct capacitance and all that crap. There's a program that does that, and I'm gonna look it up later. But I'm gonna hit Jack and figure it out tomorrow. Have a nice day. And I will leave you with this little